All right, welcome to my little discussion of how to bound causal effects. I put this one paper up there, which is counterfactual probabilities, computation methods, bounds and applications. This is one of a few in the literature before and after when people, or Alexander Barker came up writing these things down. So who's read the paper top to bottom? No problem if you didn't. I'm just trying to gauge what people are. Okay. I mean, I'm gonna I'm gonna explain all the basics anyway. And so basically, this kind of links into me trying to I'm revising some things for my research that I'm doing right now. And so I was like, two birds with one stone. And so here we are. What are the basics of bounding effects? So let's get straight into that. All right. So that stopped working. Okay. So we did actually talk about this before. I did talk about one paper in January, if you remember or not. This was a follow-up paper. This is kind of a sequence of events. So this one here is 1994 in the middle. That's the one I put up for reading. Before that, there was one that kind of phrased the idea. This one here kind of makes it tangible. This was also kind of these two papers and one or two more led to the PhD thesis of Alexander Balke. So that was 1997. And then another PhD student of Pearl also picked this topic up and put a paper out in 2000. I think there's another one now. And there's many more papers after that, but like this is kind of like the basic papers that you want to read to get an understanding of this. And so there's a repetition between these two papers, and I think this one kind of gets the best introduction to them. This is too abstract, this is like too much deep into it. And so we're gonna basically talk about this today. Starting very simply, we're looking at the problem of counterfactual query. So we have a question such as, or a statement, if A were true, then C would have been true, right? So this would have been, that indicates to you language-wise that we're looking at a counterfactual query or counterfactual statement. And so that might have this form here. So you could have, C star might be the counterfactual value, A hat star would be another counterfactual value about the intervention, and then A as we observe it and B as we observe it. So this is the actual observed world, but we want to figure out what would the world look like if we intervened this way. How would C look like? We'll clarify this a bit more. Here's another phrasing. Given that we have observed A equals lowercase a, so this one here, and B equals lowercase b, so this one here, in the real world, if A were A star, then what is the probability that C would have been C star? That's kind of like the natural language way of putting that. And so with all of these questions, we always deal with identifiability. Here I went with the quote from Hernon and Robbins, which says that when, as here, a counterfactual quantity can be expressed as a function of the distributions, so the probabilities of the observed data, we say that the counterfactual quantity is identified or identifiable. Otherwise, you say it is unidentified or not identifiable. So this is how you can, figure out the identifiability, whether you can currently identify the effect. And so two questions that come with that is obviously confounding. So do we have confounders? And theoretically, we'll always say, well, if you do have them, then just apply the Baxter criterion, and here you go. You have identified the effect. But practically, the observed confounders, the set of those is always incomplete unless you obviously have a very strong case from subject domain knowledge. And then another question is, what are the functional relationships between the variables? But that's not that's something we'll look at in a different perspective later. So just as a background, how that would go around. Oh, this is a little quiz. So here we have a graph on the right, which is a causal graph. We have here X and Y. So X would be the intervention and Y would be the outcome. Now the question is, what's the right adjustment set? So I'm just trying to show how we usually go around with confounding when we assume that we have a complete graph, for example, here. So you can see here, no adjustment would get you somewhere here. The dotted line is the true causal effect, and then adjusting by everything gets you close to 0. So any guesses which adjustment set we're looking for, which which variables should we condition on to get the to identify the causal effect. No takers? Okay, so this is halfway. So B and C, if we went for B and C, then we get down here. So obviously the problem is that C is on the way on the causal path, and adjusting conditioning on variables on the causal path opens, I think blocks the path, and that's a violation. And then here B and H, for example, here you'll be conditioning on a collider between a path of X and Y. That's also a sin. So that just leaves us with B and BDE. So if you either adjust for B itself or BDE, then you get the identify the proper causal effect. Yeah, this is actually, there's a link down here where you can play that through in the Jupyter Python notebook. Okay, so that makes it a common problem that we have non-identifiability. So what do? We just give up? No, we don't get up. We cannot get the effect, but what we can do is we can get a bound on the effect. And so sometimes these bounds indeed can also be informative. And so as far as I know, Ricardo can correct me, informative bounds basically means you don't have 0 in it as a minimum, and maybe your lower bound or your upper bound, whatever region you're in, negative or positive, is, you know, to some extent away from 0 as well. And so, for example, here's an example from the second paper that I put up. This is DC fairness paper. You can see here that we have a truth. This is the true causal effect. This is a path specific effect. We'll talk about that also later, but just assume it's one effect. And you can see here that previous method they compare to included the 0, right? So we have minus 0.26 and plus 0.26, and clearly in between those numbers is 0. So we can't tell whether the effect is positive or negative. But when we use the bounding method that I'll introduce now in the next few slides, you'll see that we get 0.17 and 0.18, and that clearly also includes the true causal effect here, and that also is positive. So obviously we wouldn't know the truth, but if we had this bound here, we would know that the effect is true. It is positive, not as true, it's positive. And so that, for example, in the context of fairness, ethical algorithms, and so forth, can be quite helpful to have a method like that. So with a non-identifiability situation, you still could find the bounds, and the bounds could be informative, leading to this situation here. So not including 0. So that's pretty cool, right? So you're non-identifiable, but you're still getting an informative bound. Any questions on that? Return to gallery view. Cool. Okay. That's bigger. Yeah. So I'm putting in blue some questions that came up while I was putting this down. These are kind of like, I don't know, what halfway research questions that really aren't validated yet. But one question I personally would have, as you will see at the end of this, if you understand the whole bounding thing, is like, is there criteria to figure out when bounds could be informative or not? So obviously, when we're like, oh, they could be sometimes informative, like maybe we can make even stronger statements, but I don't know about that. So today's menu is instrumental variable models. And so I'm going to review that here. So we'll look at the very classical case. This is also referred to as imperfect compliance, right? The statistical concept is the instrumental variable, but the common way to explain it is imperfect compliance. And so what that means is that you have a treatment assignment, a treatment reception, or the treatment received, and then the observed response. So practically, here's the example. You go to a doctor, he prescribes you aspirin, then you go home, then you take your aspirin, and then you have the outcome of the aspirin. So that's the causal chain here, or the causal relationships. But the problem is that often people get prescriptions, so they have a treatment assignment, but then they don't necessarily stick to it. So they take maybe half the value, or they don't take it all. Now, for the rest of the slides here, we'll just assume this is all binary. So you get the prescription or you don't, and then you take it or you don't, and then it has a positive outcome or you don't. And obviously, with latent factors, you would encounter confounding between D and Y. So if you wanted to figure out what is actually the effect of this drug, of this prescription, then you would want to know what the average cause effect is from D onto Y. But obviously you would also observe the z variable here. And so the problem is that estimating d on y, you again have an incomplete set of confounders, these u's here. You might not observe all of those, and then you're getting a problematic situation. That is where we get instrumental variable models from, is that when you have this instrument here, you can actually make some statements given certain assumptions on this d onto y. That's as far as I'll go into instrumental variable models. If the easy way is just to look at this, this is a causal graph, and you're observing c, d, and y. And this is specifically in this context here would be imperfect compliance, and it's also referred to as instrumental variable.
Can I ask a question?
Yeah.
So I assume this is just an example. Maybe it doesn't relate very much to what you're going to say next, but yeah. It seems like assuming that the treatment assignment is a valid instrumental variable that's not influenced by the latent factors itself is a strong assumption.
Obviously a very fair question. So that's one of the 3 or 2 assumptions you need for the instrumental variable model to work. So here clearly we see that U doesn't influence C. I'm not an expert on picking instruments. So I don't know. No. I wish I was. I want to learn more about what a really good instrument is. But I don't know. Like, let's think about it. The doctor gives you a prescription. What would be a confounding factor?
Well, it seems like you're trying to say that Z is kind of independent of whatever other characteristics of the patients that might influence the actual receiving of the treatment and the outcome. But it seems like if a condition of a patient would also make them less likely to be it seems a bit contrived, maybe, unless.
Well, maybe the example is thinking that it's close to randomized with respect to assignment.
Yeah, but why would the assignment be random? Like, doctors don't randomly assign.
Because it's a study.
Oh, if it's a study. Okay. It's not you going to the doctor. Okay, so it's intentionally just a randomized experiment. It's
right.
Okay.
But you could also think, that you may believe that you have blocked the confounders for Z, but not for D. So you may have a conditional treatment that there's something that is recorded, is documented.
Sorry, I just missed the part that this is trying to describe an RCT. Now
it
doesn't have to.
Doesn't have to.
The caption says that.
Yeah. But I didn't say it, and it doesn't have to. That's also the true part. But in this case, it is.
It's partially because it's a problem that people studied before, and it's kind of making people, if you're familiar with this, you should pay attention to that. It's also, if you have, for example, a cheaper treatment Z, but want to assess D, then you go with Z, like treating people at home instead of in a hospital. So you don't control their compliance at home.
Right, but you control the assignment, and that's right.
Yeah. So very valid questions. So I should have mentioned that this specifically shows an RCT, but the IV model does not require an RCT. Okay. So if you then would go down the route of effect estimation, you put this down, so you'd be like average causal effect of D onto Y, and then you would take the difference between these 2 probability estimates or statements. So you would have the positive outcome given you had a intervention equals 1, and then the positive outcome minus the intervention equals 0. Sorry, the intervention, that's wrong. The treatment received 0. The treatment assignment here, as you can see, is obviously not part of that, not yet. And so that means you would have to then figure out these 2 values. So by Pearl's, or by the graphical model factorization, you would want to take the sum over the expansion onto U. But obviously the problem is that we observe all of these. We want to observe all of these variables. So this marginal here with Y, D, Z, and U, but practically U is obviously unobserved, at least some of them. So they're latent. And that makes this whole thing unidentifiable. But what we do observe practically though is the marginal here on Y, D, and Z. And that will be helpful, as we saw in a second. Now, clean your brain. This was the IB, put it back on the shelf. And now we talk about a new idea. And so this is called response functions. And I'll try to do this in the best way possible. There are many ways to do this, but I just put this together last night, so we'll see how this goes. This is kind of the core message of this whole talk. So if you listen now for the next 2 minutes, then you will have nailed the main part, and then you can also leave. No, just kidding. But nevertheless, so this is really important. So in the standard causal model, we have a node, a variable v, and then we determine the value with a function that takes 2 parameters, which is mainly the parents, the values, and then the UVs, I don't know, how do I say that?
Exogenous.
Exogenous variables. I actually just figured out, realized that I don't have the best terms for this. And so when you look at this, but let's just move on for now. If you look at this, you can see that UV can be anything if you don't restrict it. So it could be any type of any domain. It could be, many thousands or infinite values. But by the definition of how, we determine the standard causal model, we know that for each instance of this UV variable, the functional mapping from the parents to V, so this value here, is a particular deterministic response function. So while you might have a lot of these or infinite of those, each of these values does actually map the parents' values to the actual node value. So there's the parents and the use, and together they determine this value. And so for every value of this one, combined with every kind of combination of this one, you have a deterministic value. So I'm not explaining this the best way, but I'll have some more ways to look at this. So I hope this will run it home. So if you think about the consequence of this is that you can map each value of UV, so a lowercase uv, to a deterministic response function. So what that means is that you have all these combinations of u's and p and v's. And so you could actually phrase how that influences the value of v given the parent's value. So you could look at uv having a finite amount, finite number of states, and for each state we could have a characteristic or deterministic response of this function here. It might sound all still weird, but I have very practical examples coming up that hopefully make this clear. And so the reason for this would be that although the domain size of UV is unknown, which might be very large or even infinite, the number of deterministic response function is known, and now go away Google, and limited, given the domain size of P, A, and V. So UV can be unknown. So if it's unknown, it can be large or infinite. But if you look at the response functions, that can be known and limited. And so that makes it all tractable. So let's see what that means. Yeah, so there's another research question, but we'll skip that for now. So what that means is that we can kind of re-parameterize this causal model. So here's again the IV model, or the imperfect compliance, and we're now going to replace we're now going to add some response functions onto the nodes. So this is a way you could put this. And so what that means is that specifically here in this case, what people talk about in imperfect compliance is that, complying to the treatment assignment. So Z here is not perfect, hence it's imperfect compliance. And that also means that you have 4 definite responses in a binary case. So let's walk through this. So listen to this, 4 definite responses. So you have response 0, 1, 2, and 3. And so the Z variable here will always give you a 0 or a 1, because that's how it's defined, right? You get treatment or you don't. And so the way D is going to respond to that, so the response function of D has 4 values. And so let's take a look at number 1 or number 0. We could have an always taker. So that's a person that will get a prescription from the doctor, and then regardless of what the doctor said, they'll always take it. So C could be 0 or C could be 1, but A, or this should be D, I'm taking this from somewhere else, imagine this is D will always be 1. So let's say the doctor says, take aspirin, I take aspirin. The doctor says, don't take aspirin, I still take aspirin. I'm an always taker. That's the first response, indicated here by index 0. The next response would be a never taker. So the doctor says, take aspirin or take it down. Regardless of what he says, I will never take it, so I'll always be 0. That's the second response function. So just think of the possibilities. This is really an exercise of combinatorial permutations. Then the third one is a complier, right? So this person, when the doctor says, don't take aspirin, you don't take aspirin. And when the doctor says, take aspirin, they also will take aspirin. Now, who's left after that? So we get the always takers, never takers, compliers, and defiers. So these are the people that, I don't know, I always think of like some, I don't know, very extravagant person. I don't know, so someone who defies, you know, all the orders. So the doctor says, don't take aspirin. They're like, oh, I'll definitely take aspirin now. And then the doctor says, you know, the doctor says, take aspirin. And then you're like, oh, I'll definitely not take aspirin. Tinfoil hat people, I don't know, you know, whatever. So this is kind of the combination you have here. These are the 4 definite functions if we assume that this instrumental variables has only binary domain values. This is it. There's nothing more than that, really. And so this gives you, in this case, the response functions. So let's put this a bit more mathematically. Here again, have 4 functions for D. So this is D right here down here. And so it has 0, 1, 2, 3. And then here, if my D response is 0, then I'll see this is indicated as D0 here. I will not take the drug. So this one here would be a never taker. So regardless of whatever happens, this value is already predetermined. Then we have an always taker here, so indicated with a 3, that is always D1. Now then we have these ones here, right? So these compliers and defiers. So the complier, when Z is C0, D will also be 0. So you don't get the aspirin prescription, you don't take the drug. And so as a consequence, obviously the last one, the defier, will have, you know, when the doctor says don't take the aspirin, you will take it, and so forth. So now we've just replaced, or we've at least created, the finite set of response functions for this binary IV model that would help us reparameterize this whole causal graph. There are different ways to put this. And so what we now come to is the step where you replace U with R. So we start here out with the normal, you know, function that determines the value of V, which takes the values of the parents and the exogenous variables UV. And then we'll replace this with R. And so this replacing process can be formulated mathematically in different ways. This one is the kind of most concise and rigorous one. The one you read in the paper might look a bit different. And so I'm just putting this here, and this is maybe too complicated for a first start to understand, but just imagine you replace this UV with the R functions, the response functions, and you can just look at GV being a composition of that original function and this inverse function here, LV. Actually, I think I didn't put LV here. Let me just pull that up. Yeah. Yeah. So LV here is a function that takes exogenous variables and then gives you the corresponding response functions. So apologies for that. And then what you end up with is that you need to create some kind of indicator function that helps you assign which response goes with which value. And so let's say this again. So which response of this value, right? B has the deterministic values. In our case, it's 0 or 1. So if we had the outcome, it would be either 0 or 1. Let's say you know, aspirin is successful and aspirin is unsuccessful. And that one has to be matched with the response functions that correspond to that response. So this is the verbal phrasing. You know, you're just looking at me listening. I have some graphs that show that more clearly. And so the way to do that is with an indicator function that basically says, you know, yes, if that GV here, which takes your parent's value and your response function, does indeed match your value, and says 0 otherwise. So we'll get into this right here. These are some other phrasings. I'll jump over that. Most easy graph here, okay? We have X and Y, and UX and UI are correlated. So that would also be here, you know, this classical wall graph. It doesn't get more simpler than this. We have X and Y observed, that's the marginal here. And now we want to match the observed variables with the corresponding response functions. And so I put this here as the formula here, and here again, we see this indicator function. If we go through this here, we can see that we want to take the sum of all response functions of the probability of this response function. But for every response function, we only want to count it when it indeed also does correspond to the observed value at that point for the response function and the parents. I spent a lot of hours on like going through this again and again until it clicked, and then I understood what that means. So here, I've drawn this out, and maybe this will help. So you can see here, we have the IV model. I slightly tilted it. We have C, D, and Y, and the corresponding response functions. And then we have here the observed marginal. So that's C, D, and Y. Everything is binary. And then we have the unobserved response functions. All right, so these guys are unobserved. Now, when you think about it, if you have a binary C, D, Y, that gives you 2 to the power 3 states, right? This is literally, I just wrote it out here. So you go from 0, 0, 0, all the way up to 1, 1, 1. These are all the possible observed states of your IV model. So it could be the case that this one has a probability of appearing, I don't know, 10%, or 10%, yeah, 10%, do you say that? 10%? This one could be like 5%, and then as a whole, they need to add up to 1. And that's pretty much it. And so now we're trying to match up all these value combinations with the corresponding states of the response functions. And so this, obviously, this is hand drawn on an iPad, but we can actually follow through with this. The response functions here, we know the states they can have. So you can see that RD has 4 states. We just figured that out before, right? You have someone, you know, that is always taking, someone that's always defying, compliers, and so forth. And so we're now just going to make this permutation here of all these different states. So how many states do we actually see here? Well, it's 2 times 2 to the power of 2 times 2 to the power of 2 that cut up here. So this is.
Do we make a positivity assumption that no possible ZDY occurs with probability 0?
Yeah, we do that. Okay. Actually, yes, positive 0 is 0. I probably misunderstood your question.
Well, that looked like they did allow for 0 because it's greater than or equal to. No?
Yeah. So, what do you mean by positivity?
Positivity, I mean no vector ZDY. The probability of any given ZDY vector is bounded away from 1 or 0. That's what I mean. It's just that they, yeah, it comes up.
Yeah. No,
essentially, that you observe all possible.
Yeah, so that's a better way to state it. Yeah.
Well, P is given, so you're assuming that P is just what you observe. P of ZDY. There's not a free parameter. The free parameters are the distributions of the responses.
Okay.
So the model may or may not fit. So you can actually falsify this model. So you can say there must be an edge between Z and Y, for example, but only in certain cases. So it's sometimes, if you don't falsify the model, it doesn't mean the model is correct. So this was the idea, this is actually the idea behind Bell's inequalities. So that's what John Bell did. He set up a latent variable model. He put some constraints on, so you know, Bell's inequality from quantum mechanics, put some constraints on how observations could respond to latent variables, and they showed these constraints are locality constraints. Then he showed this cannot hold because the joint distribution that violates the constraints implied by this model. So they're very nice. The paper I mentioned before this, what's it called, inflation technique, it was written by people who work on quantum mechanics. So they explain, there are actually papers written by Pearl and by James Robbins that address the Bell's inequality directly. You can actually see a few papers on people showing that, the link between IV models and Bell's inequality. But it's a more general problem.
Yeah.
So P is given. What is not given is what the latent variables, how the latent variables is distributed.
I was not aware of that link actually, but that's very exciting. So that's really. Yes, so this is just observed. This is just data you collect. Of course, in some cases, there could be systematic prevention of certain states. I can't figure out one right now, but maybe ethically it's not allowed for people to, like, I don't know, take.
Yeah. There's some distributions that are just not compatible with the IV structure. So if you try to test the constraints implied by the IV distribution, they will exclude the distribution that you see.
Yeah.
So not every distribution is compatible with the IV structure. Not every 2 by 2 by 2 conditions table can be parameterized by IV model.
No. But I guess maybe the more practical thing, or I don't know, maybe does that solve your question, David?
Yes, thank you.
Yeah, okay. So this is not a perfect thing, but just imagine that so every 2 values of R and D, so 0 and 0, can be combined with 2 values of RZ. So this one here is actually, this would be one path, or this would be one path. I apologize, I just improvised this diagram. But what you can see here is that, for example, if we observe Z, D, and Y, all of them is 0, then we can assign them to 4 definite response function states. And so we have here, first of all, this line here. So CDY observed as 0 also fits RZ, RD, and RY 0. So if these response functions here are in the state 0, 0, 0, and this also corresponds to this 0, 0, 0, then we also can see that 0, 0, 1 corresponds to that. And so how am I pulling up this table here? How do I figure that out? Well, you can just write down, okay, Google just, there we go. You can just write down, for each of these kind of responses, you can just write down these functions here, and then you can just follow through with them. And so what you're trying to do is you want to try to find the value combinations here that match the states of the response functions. So let's figure this out. We know zeros are, I think, let's see, what are they? Zeros are never takers. Okay. So zeros are never takers. So if these are all in zeros, that means that at any point in time, Z will be 0, D will be 0, Y will be 0. So that does indeed match an observation like this one here. Now, I also match this up with 0, 0, 1. Okay, so what does that mean? That means that when Z is 0 and D is 0, then, so in terms of the response function, then when D is 0 and the response function is a never taker, so it will send a 0 down to Y. And then Y, if it's in the state 1, it is a complier, which means that it will do whatever D does, which is 0, right? So the response function state of 0, 0, 1, so 0, 0, 1, means that effectively Z, D, Y in the value determination are also 0, 0, 0. So whether you have response function state 0, 0, 0 or 0, 0, 1, both of them will give you an observed value of 0, 0, 0. I'm saying a lot of zeros and ones. I don't know if you guys can follow me. I'm trying to point it on the screen here. Now this you can do for further 2 values, and by the way, this is just the system is set up. Every observed state has 4 response function states associated to it. So you have 8 states in terms of what you can observe in terms of the values, and you have 32. Is that 32? 4, 8. Sorry, 16. No, it's 32. You have 32 possible states of the response functions, and so every observed state gets 4 different combinations. So you basically kind of like zoomed up. You made the system more granular in a sense to make it to describe it in an intuitive way, and so you kind of like look deeper into the model to look at the different responses that lead into observed values. So think about it this way, you know, if you observe z, dy all being 0, you can now say that this could have happened due to 4 causes, right? Due to 4 different states of the response functions. So I can't tell you which one of these 4 different response function states led to the observation 0, 0, 0, but I can tell you that this is finite, and I can tell you that these 4 different states have led to this as a combination, or maybe just even one of them, and so forth. Does that make sense? So again, it's not really that complicated. This is really just an exercise in combinatorial permutations and just matching things up. You can do that by hand here like I did, and I'll show you later how you can do this automatically.
Yeah, isn't the complex of that super exponential? No, I think no, yes. The complex of this is exponential, then transforming that into a corresponding dual representation that is exponential on the size of the input. So what I mean by this could define the vertices of the extreme cases. And all the probability distributions compatible with that is in the convex hull of it. So the exponentially many vertices, and the way they convert that in terms of inequality constraints on P of Z, D, and Y is also exponential input. So it's a super exponential problem to try to write down all the inequality constraints implied by that in P of Z, D, Y.
Yeah.
Exponential the number of states and the number of variables.
So making an example of exactly that point later, where you can see how this kind of blows up exponentially. All right, so let's get going. And somehow there's a problem with my Google when I don't focus the cursor, but nevertheless. So simple example coming back to here. So you have your X and Y. X is influencing Y, you know that from the causal graph, but you have confounding here. You can now match, you know, your observed state, right? So this is observed, this is unobserved. You can match this observed here state, this marginal here, this turn distribution, with your response function representation of the world. So what you do is you go through all combinations of the response functions in X and response functions in Y. You can just write them all down, or, you know, create a permutation table. And then you can say that you can connect. I use these words that are very tangible and physical, but that's what you effectively do. You can connect all the response functions that, you know, are associated with that state. So these indicator functions, you know, when both of them say yes, both of them say 1, that means that, you know, this combination of response function corresponds to that state of the observed variables. So, you know, in this case, the indicator functions went through this 32 times. So when we pulled up the table here, we have 32 different combinations, and 4 times it said yes when we looked at 0, 0, 0, and 4 times it said yes when we looked at 0, 0, 1, and it said yes to these combinations that match the response functions with their states. You can do the same thing then for the causal effect, right? So now you have an ability to express any probability statements about this graph with response functions. And so when we want to figure out the causal effect, for example, here from X onto Y, so this is the total causal effect as they mentioned in the PC fairness paper, then you can just take the probability of Y, you know, the counterfactual outcome of y given x1 and y minus y given x0. And so this then also, again, just comes down to a very practical use of indicator functions. And so in this case, you want to collect all the response functions or response function probabilities that are associated with, the first potential outcome, the first counterfactual outcome here with the treatment, and then subtract all the response function probabilities where the response, where the treatment was 0. And so it's a very flexible framework in that respect. Okay, so when you set out all of this stuff, then you can put together linear programs. So this expression here, these expressions, they're all linear, which means you can use a linear optimization. And so you can minimize or maximize this objective here, for example, your causal effect, and then just put some constraints on them. And so the constraints are basically that your variables have to match, so your observed variables have to match the response functions here. And then we also, with the probability statements, all the probabilities of the response functions together have to equal 1. That's just the way probability theory is set up. And then we also need to make sure that they're all positive, which is also a requirement from probability theory calculus. And that is pretty much it. So the first part here, you match the marginals, you connect the observed quantities with the unobserved quantities, where the observed quantities are the actual variables, for example, binary, and the unobserved ones are the response functions. And then this one is just a probability simplex. Does that, any questions on that? Cool. So practically, what you'll be looking at then is that, this total cause effect would be the objective. This is a function that you can write down in code. And then this matching here is a constraint. This is also something you can write down in code. So put it in words, the key idea is to parameterize the causal model using so-called response functions. So we replace the U's with the R's. And then the distribution of these response functions captures all randomness encoded in the causal model. That's the first statement. And so with that, we can explicitly traverse all possible causal models to find the tightest possible bounds. So what time means we'll define in a second. But imagine it, you have all these different response function states, which show you different causal models. And now we traverse the ones, and whichever one is the worst in terms of the minimization, for example, of the causal effect, that is also the lowest bound you can get, right? It doesn't get worse than that. And so when you then maximize the objectives, that will also give you the highest one, and that will give you 2 tight bounds, where the cause effect is definitely somewhere in between here. This is obviously very simplified. You have binary values and so forth, but it's definitely in between these two. And I lost my thing again. Okay. All right. So
can I ask another potentially naive question? What if you're traversing all the possible models, and some of them are informative and others are not? So it's like the worst case is also, let's say, not informative, or multiple of them. So do you just like ignore them, like at the outset, or does it not happen, or?
So I guess the problem is that while you might hit some models that would be informative, you wouldn't know whether it's the true model. So you want to go for the model that's the worst, because you're certain that the worst model, it can't get worse than the worst model.
Yeah, no, that makes sense. Yeah. But like, would you have, for the worst model, could you have bounds that include 0?
Definitely, most of the time.
Right. Okay. So the kind of worst model would usually, or would often give you non-informative bounds, is what I'm saying. And then like, do you just go ahead and ignore those, or?
Oh, I haven't used those yet. I don't know, Ricardo.
There's not such a thing as it's non-informative with respect to what, right? This is
I don't know.
All the information you have in your assumptions.
Okay, because I thought that was the definition that Jacob gave her.
I put that there, yeah. So
right, that's what people. Yeah, what people typically say is the bounds are too wide, or they don't include zero, then they're non-informative. But then it's not the method that's not informative, it's your assumptions are not informative.
True wisdom. Yeah, so I put that there because
wisdom.
Yeah.
Know what you don't know.
Yeah. I oftentimes see like people say, you know, this is only useful if it doesn't have a zero in it. Obviously, it's you know, as informative as you interpret it.
Yeah, there's this obsession for some classical statisticians or maybe some people in particular applications that if it cannot distinguish from zero, you have learned nothing. But it's a bit. Well, I guess if you're working in a domain where effects are super tiny, like in many epidemiological domains, what you want to know is are the effects positive?
Yeah.
Don't even care about saying what effects are, because everything has a small contribution to your whatever morbidity outcome might be. So all they want to say is there's evidence, there's a positive effect, because this is really what I can aim at.
Yeah. Yeah, so I think that's the way, not a naive question. It's a good question. Yeah, so just to put this back into context of identifiability, an unidentifiable situation means that there exist two causal models which exactly agree with the same observation distribution. That's something we go over again and again in the Pearl book. But that's also the case here, right? We have an unidentifiable case. We have many causal models, and then we choose the worst as the lower bound. Okay, and oh, it works. Okay, I put another diagram here. Boy, this is just a screenshot. Don't judge me. This is a simple optimization just to nail this point home. I just put together like last week. So here you see a very simple problem, optimization problem. These are the heat map gradients, and this one is the perfect value here. So let's say that's the minimum value, and you start somewhere here on this field, and you want to go down here. You can do your gradient descent. Obviously, watch out. This is not a linear program. This would, this is just a very intuitive way to look at it. A linear program can do vertex enumeration, which is much more efficient. But let's say all of these would be possible causal models, and then we just kind of find our way to the worst here, and then you would also see kind of the bounds, like, slowly jump and then find its way there. That's just a very intuitive point. So this would kind of represent models on the way to the worst models. And so then you basically, this is the exact causal bound from the Pearl paper 1994. And so this is how I recoded it, and then you can see how it like optimizes here. Again, this is actually not a linear program, but it's just for illustration purposes. Here then you can also see the values of the 16 response function states that are associated with this. So these are latent variables, and you're seeing here the estimated probabilities. Actually also, I just realized, nice to see how they actually violate the constraint of probability temporarily then to all be between, actually all to be positive, so between 0 and 1. And so you can see how like it kind of, clocks into the combinations of probabilities for this response function. And so just as a reminder again, so like a combination of 4 of those would represent one observational state. And so the probabilities together would then represent the probability of that state. Okay. Then here's something I haven't fully figured out there. I'm just putting that for completeness. So proving that the bounds are tight. So first of all, what does tight mean? Well, so there's a paper 2020 by Michael Sachs, Sweden somewhere, I think Karolinska Institute. And he says, so tight here means that all values inside the bounds are logically compatible with the true distribution of the observable variable. So don't confuse this with confidence intervals or something like that. This is not related to that at all. It usually just means all values inside bounds are logically compatible with the distribution. And so if you use your permutation thinking again, compatible is very nice to see with like binary values. You're just like slotting the things in, and then at some point you just look at the ones that slot in nicely.
So what was it? I blink. What is their claim again? Proving what true?
Yeah, so this is something I wanted to ask you because we discussed this briefly, and then we kind of said this is just statistical software paper really, but so they made this point that to the knowledge of the authors, so 2020 paper, no one has proven this is true. And so they say
what it is true?
That these bounds are tight.
So which, sorry, I blink, which bounds?
The tight bounds that come out of the LP, the linear program.
Well, by definition tight, right?
Yeah, I know, and I still don't know what yes, that's why I say, is this actually a proof of tightness of bounds? Like, isn't this just,
it's by construction?
Yes, do you say tautological? Yeah.
Yeah, I mean, which paper is that?
That's Michael Sachs et al., the 2020 that we discussed briefly, the one that I spent a lot of time on, only to digit. I have it here. It's the causal bounds methods paper. Symbolic computation of tight causal bounds. The one that got the European, the Eurosim.
Oh, maybe it's talking about his bounds, not the LP bounds.
I think he's talking about the LP bounds. So let me.
I think what he has might be, because the LP can be, just several people have developed ways of finding bounds that's not LP based, but they're not guaranteed to be tight, because it's just computation more tractable to try something else, which is symbolic.
Yeah, that's not symbolic.
I mean, typically they do symbolic computation. Many of these papers are symbolic in the sense they have algebraic methods of transforming the LP into symbolic constraints that involve only the observed variables.
Yeah.
This is, David, this is a thing related to Tarski. What's the name again? Tarski's. It's a classical result from algebra from early 20th century that you can quantify eliminations. Quantify elimination in this case means remove everything about the latent variables, only describe everything in terms of the observed variables. So instead of having that such that linear constraints with PR, you try to eliminate PR and describe everything just in terms of the observed distribution.
Yeah.
So this is symbolic in the sense that they derive explicit constraints, like those ones, explicit constraints.
Yeah.
And this is very expensive. This is a super exponential problem.
Yeah.
So people who try to avoid that, they either go purely numerical, or they try to find things which are not tight by looking at particular constructions that sometimes may be tight, sometimes not.
Yeah. Yeah. But I thought, so let's see. So I think I rephrase this here. So what he says that linear programs are guaranteed to find maxima and minima if it's a linear program. So if we can show that a DAG and a target query create a program, we can guarantee the tight bounds. That's his proof. His proof is he has an algorithm that creates a linear program. If you stick to these constraints, it's a linear program. Therefore, the tights are bound. The bounds are tight because
by definition, just say match.
Yeah.
I'll match the distribution using this complete parameterization.
Yeah. So this is actually a proof of tightness of bounds. This is no need for proof. I mean, the proof is in the linear program. This paper is written very overly complicated. And so if you ever are more interested in this, just read the PC fairness paper instead. That one is
it's a much better written paper.
Much better. So yeah, so as mentioned, if you then would go down the route and use the linear program, you can actually use some symbolic. You can get some symbolic representation of these bounds, and this actually has been done manually. I think manually with some people like in epidemiology and so forth, but they have a very specific problems. They wanted these bounds. They would go down, and then like at the end of the paper, they would present these like this, and they're like, yeah, this is our result, and this is what we use. You can also obviously make this automatically. And so this is actually what the stats data from 2020 I put together. So they went all the way to make like a shiny app where you can put into a graph, and it will give you all the different symbolic terms. It is loading, yeah. So you can play around with that sometime. You can connect it or something. I don't know. And then you can, yeah. Okay. Nevertheless, that's not the focus today. Okay, so so this is where I show you the code to make it like really practical. If people have a time constraint, I would just skip to a few last messages if I have. If you guys, all of you have like still 10, 15 minutes, I would go on and to show you quickly what I've put together in terms of the code.
I mean, I'm kind of curious.
Yeah, all right. So this is something I've been putting together for 4 or 5 months now. And so this is basically, I have a causal Bayesian network here. It's a class with the values and domains and blah, blah, blah. And then on top of that, I put something called the bulk graph. So this one just inherits causal Bayesian network capabilities. Oh no. My external display just disconnected. There we go. I think for you, probably nothing flickered. Maybe it did. No, I think the screen sharing disappeared. Did it? It's still on?
We can see the code.
Okay, so it soon tells me it's not screen sharing anymore, but if you can see that, that's fine.
It is.
So long story short, I can read an imperfect compliance graph. So this one is the imperfect compliance graph. I'm going to run this in debug mode so you guys can see like what it all creates. Actually, let me run it once just by itself. So this one takes the bucket paper probabilities, assumes there's this debug graph, the causal graph, so that you can see this is just a simplified representation. So you have 0, 1, and 2. That would be Z, D, and Y. This is what's in the causal Bayesian network, and then it goes through all of these calculations here and finds the real graph. Apologies. So this is the true lower bound, and so this one gets almost close to it. That just proven to you it works. But let's see the real capabilities here. So I have my graph here, my bucket graph, and I say calculate bounds, and then it will construct the response functions. And so what I've done manually here before, if you remember, so this one here, right? This one here, you could do that all by hand, but you can also just do that all with permutations. It's actually just what, 2 lines, and that gives you all the permutations of the response functions. And then based from there, you can then put you create a joint table on the distributions if you haven't pre-specified them. All of this probably doesn't make any sense to you because I've spent so many hours on this and you don't know what, reading other people's code is the worst. But we get a linear system, we get an objective, and you punch it into optimizing it for a linear system. And this is something maybe more applicable. So you see here, I have these constraints. This is the matching of the response functions. So this one is an observed vector of variables. So this one would be these probabilities here. So this one here, each of these combinations has a probability. That's on the right side here, and then on the left side, I have the response function multiplied with a matrix that indicates which. This A mat is basically all these lines here. And then we have just sum to one probability simplex and positive probability simplex. I'm using a CVX because I like it. Obviously, you don't have to do that for a linear program. But then you just optimize, so you minimize, maximize, and you get your lower bounds. And actually, I just want to show like literally how these matrices look like. I think it's just really nice to see that. So we're gonna run again, but in debug, and that will stop me at the corresponding places. All right, so this is the objective. So this is how an objective looks like, right? So imagine this is how it looks like. These are 16 response functions from 0 to 15. And so what we're saying is we want the first, or like response function 1, we want the positive of that, and then we want to take away this value, and then here the positive and that value. And you want to optimize this combination of the response functions, and that is literally the total causal effect. So it's literally just a vector, a binary vector, well, not binary, sorry. It's a vector that just indicates whether you want the positive, so, you know, the left side of the total causal effect or not. So let's make this a bit more tangible. Here. So you have this left side here. This one here with these indicator functions will generate all these red values here. And then the right side here theoretically generates with this indicator function all these negative ones here. So basically this indicator function 4 times out of 16 times will say yes, and say this is the positive and so forth. And then the same happens with the AMAT. So you can look at this here. This is a bit bigger. This creates these, you know, beautiful patterns. And so you can see, for example, that the observation 0, which is 0, 0, 0 for CDY, is associated with 4 response functions here. So 1, 1, 1, 1 for these. And so you can just see how it just combinatorial, you know, permutations just goes through and connects each of them in this corresponding way. And then these ones here are just simple identity matrices with the constraints. Okay, that's the most simple case, right? Imperfect compliance. Now, let's see if that matches up with my slides. Oh yeah, one more point is that you can add more assumptions by additional constraints. So if you have monotonicity, if you think about the always takers, the always defiers, the compliers, and so forth, these 4 states, monotonicity means that you don't have defiers. So you could just implement this constraint here as an additional, this assumption as an additional constraint in your program. And I'm going to go here. So you might be like, oh, this is great, Jacob. You just did IV models with response functions, but can this do anything more? Yes. So we saw how we could, you know, create response functions for this graph. We could create it for this graph. In fact, we can create it for all kinds of graphs, in quotation marks, because there are some restrictions. But here's a more complex graph. And so we can go through this here. Actually, this is a little exercise, so I'll skip over that. The number of response functions per variable is actually determined by this very simple equation here, which is that it's the number, the size of the domain to the power of the domains of the parents. Now, what does that mean? And now we come back to super exponential growth, is that S has 2 response functions, W has 2 to the power of 2, A has 2 to the power of 2, and Y has 2 to the power of 2 times 2 times 2, which is 256. Now, obviously, no one is going to write it down by hand, and that's why I mean, that's not exactly why this program is built. But how many response function states gives you that for the whole model, where you apply all of these, and that's 8,192. And so that's, you know, quite a lot. So we can see that here in this case. So what you're seeing here on the graphic, this graphical model here, I'm loading this in here with the D1 observed model, and so we can run this here again, and you'll see obviously that this will take a bit longer as well to run. So this is how it looks like. You know, please don't judge, but this this is just random every time. I haven't put in the preferences, but this is as it goes into Y directly into W, W goes into A, and so you see how this matches up with this one here. And there are also 2 causal bounds to this. And now this is running, and eventually it'll tell us that we've matched it. I'm just going to finish it now with the final part of what I've put here together, which is to go beyond these more simple effects. So we've just been talking about the total causal effect, which is just counterfactual or potential outcome treatment, you know, minus potential outcome control. But there are more effects, right? So there's a path-specific effect, which is basically that you only want the effect along a specific path, and then along the remaining other paths, you keep it normal, you keep it in the control. Then there's counterfactual effects, where you condition on a real world value and you want to know the counterfactual value. And then there's path-specific counterfactual effects, which is combining these two here. So this is, for example, the path that's being used for this diagram. Now, this is finally the PC fairness table here that you see here. So if you've read this paper, you've seen this table. And this one just shows you how this is really just coming down to some kind of plug and play system. I'm sounding like a salesman, but you have your counterfactual values here, so these O's, and you can choose whether you include something or not. And then you have your path indicated by pi that you can also choose to be some kind. And so if we talk about the context of fairness, you can see how there's 7 different effects that they're listing here that all come down to the PC effect, the counterfactual path-specific effect. So what that means is that if I have a formulation of the counterfactual path-specific effect, but I plug in no O's and no path, I just reduce down to the total causal effect. So when you're just trying to set up a software, as I did, where you read in any graph and you want to have a combination, like you want to choose whatever effect you want, you're basically just looking at a very simple way to program this, is that basically you just have the path-specific effect, and then you indicate whether you will have paths, and then you indicate whether you have a conditioning set. So in this example in D1, we indeed are having a conditioning set and intervention paths, but with the very simple bulky one. So bringing back the PC fairness paper back to 1994, we just have an empty condition set, an empty intervention path set, and then you just plug that into the method here, and it still gives you the total causal effect. And so what this is all based on was based on the PC fairness. They wrote down a little algorithm here. This is the text version, but this is what it comes down to. If you take that and you program it all up, you get this very like spaghetti-like function. I'm trying to find it. It's not here. You'll see it when it comes. This one here. So all these if and else branches and for loops, I've tried to reduce it in the most, rigorous software engineering way, but you can't really get around this unless, I guess, you do a new kind of mathematical formulation that's even more like abstract. But you start here with like iterating over all response function states, and then you check what kind of effect is, and then you condition and blah, 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 blah. And then you end up with a linear program that you can then optimize for lower upper bounds. I think that is it. Yeah. So thanks for listening. That was kind of a summary of response functions. I hope that was kind of inspiring to see like how you could handle non-identifiable situations. Obviously, there are some limits here. I put some down here, some points down here. I don't know what the criteria for informative bounds is. How do we deal with exponential increase in response functions? This is all discrete. This is actually, I guess, links slightly into Ricardo's paper with Nikki. So I think that you were looking at a continuous X function.
Yeah.
Actually put that here. And then, so what does it mean to have a proof of type bounds? Obviously, that's a question mark. And then I think another thing that's really interesting is the uncertainty around these type bounds. So obviously, when we have, for example, in the IV case, when we sample these 8 probabilities on the 8 different states, there's going to be a sample, which means there's going to be uncertainty, which means that we could create some bounds around these bounds. I don't know, Ricardo, what thoughts you have on this, but how would that?
There's already some work from Inbis and Munsky from the early 2000s that does that. And the basic idea is just propagate uncertainty. You don't create a likelihood function per se, just think in terms of you have uncertainty in observable distribution. You plug, if you plug the observable distribution, a linear program get about. Now imagine just sort of bootstrap, so to speak, that data set can plug multiple inputs to different linear programs, and then by the end of the day, it spits out a different bound. So you can propagate uncertainty like that.
Yeah.
Just some technicalities, I think. I think she wanted to do some, if you want to do rigorous bootstrapping, I think there's some technical issues because bootstrapping doesn't mix too well with maximization problems. There's a paper by Ramsahai and Loritz and Biometrica, which try to do this more properly. I don't know, I mean, even from 20 years ago, people already knew a little bit how to do that in some contexts.
Yeah.
So what I did once with Robin Evans was the dumbest thing you can think about it. Just create a different likelihood function. We don't force the constraints of the IV model there. Actually, you had some ways where you look at special cases where you knew the model is not falsifiable. So there's no need to do anything complicated in the likelihood function. But you just did Bayesian inference on black box. You sample from the posterior. You fed to a linear program, and it's beta posterior over bound. It's just a function of the distribution.
Yeah.
It's computationally extremely intensive, right?
Yes, yes.
Because you're running a linear program for every single sample of a Markov chain. Of course, you don't need to, if you have a few Monte Carlo samples, it might be enough, right? Even if you have a very long Markov chain Monte Carlo, you can thin it to get independent samples. And it can get a reasonable, a not crazy number of samples to get a reasonable certain estimate of the confidence intervals.
But yeah, that's exciting.
Yeah, so there are brute force approaches for that. It's where they can be more clever about it.
Yeah. Yeah, so pretty much that is response functions. I mentioned response functions because this is kind of, the core part to all of this. Everything after that is just boilerplate. You can just get your CVXPy. You can just wrote down these constraints in the software, and it will just do all the rest for you. But constructing these response functions is, especially in an automatic way, that's kind of the challenge I took on, and then wrote the software based on PC fairness. I didn't do anything new. This is the funny thing. I haven't figured it out, but the code here is based on PC fairness. But when they've used this code since 2017, but they've never made it abstract. So whenever they write, I think they have 2 or 3 papers where they use this, and for every single one of those, they wrote all the response functions down, like hard coded, which I thought was really weird because it's such a simple step in thinking to go one step ahead and be like, I'm just going to make this programmatic, but somehow they didn't. So because I was going to deal with this for a longer time anyway, I went that way and did it. And there's it's very limited. There's some more caveats to what this stuff can do, but basically any graph that has a common confounder on all variables, that is what I can handle with this. So all I need basically is the graph, the assumption that they're all confounded, and the domain size and the observed probabilities. That's pretty much it. So then you can get all these bounds. Yeah. So yeah.
Sorry, do you have something else?
No, you could continue.
I can say that for the continuous case, we just have to use some sort of Monte Carlo method because you cannot really assess the integrals to begin with.
Yeah.
So use Monte Carlo with things like ways of doing gradient estimation. So you optimize the bounds on gradient-based methods and you estimate the gradient. And the continuous case, you have to make extra assumptions about the shape of the response functions. You just say it's a function, then you always get vacuous bounds. You get zero information. But if you just make a very, very mild assumption, like the number of discontinuities is finite, then you already get non-trivial bounds. You get something that adds on top of I'm talking about the IV structure. You get something on top of the assumption that there exists a joint distribution.
Yeah. I'm still reading through that draft.
I have an archive draft of that.
Yeah.
It's already a translation of some other work by some econometrician. So this part of it is a translation.
Concilius, right?
Yes.
Yes.
Sorry, which paper are you talking about now?
Nikki Gilbertus put a paper on arXiv a couple of weeks ago, a class of algorithms for general instrumental variables.
Yeah, it's up there. There we go. Oh, look, it's a beautiful animation. Yeah. So everything I just told you is the basis of what Nikki then uses in this paper. Just in like taking it into a continuous. What does say class of general instruments? Yeah. So basically, what if X is continuous? Or I guess the.
His code is already online, actually.
Coming soon. Oh, there it is. Oh no, coming soon.
It's not online. Yeah, okay.
You got the emoji game going.
Oh.
Here.
Okay, I thought it was online already. Sorry.
No. Yeah. So, well, then this is official here. So this is the follow-up from that. So yeah, that was the whole intention. So I hope this was somehow useful. I thought this was very, very different from like the other stuff that's out there. You know, you can like do all kinds of parametric assumptions and the usual instrumental variables and finding all the confounders and so forth and potential outcomes and graphical models, approaches to like dealing with confounding and bias effects. But like taking a step back and like trying to figure out bounds, and obviously this one is very simple, is a kind of a different way, and I've been liking it so far quite a bit. Yeah.
Part of the idea is you can use other ways of modeling imperfect interventions in minimal. So one of the things Jakob is doing is modeling perfect interventions using these ideas.
Yeah.
So we have an array of possible interventions and different trade-offs. There is the perfect intervention, that's the simplest one, but the most expensive. So we want to leverage data from different types of interventions. Again, it has to be relatively simple structures. One of the things that you get from this is it literally takes a black box estimate of a distribution. And can literally just apply, it literally takes a black box estimation.
Yeah.
You can take, for example, pieces of a bigger model and then calculate bounds on different pieces and try to put them together, because with one, solving a bound for one problem can be used as a constraint for another problem.
Interesting.
So if you have something that combines an IV model with a model that is similar to a front door criteria, but you can put constraints on some edges so the edges are not too strong.
Mm-hmm.
You can combine the IV part of it with a weakened version of the front door criteria. So you can get different margins of it. You can say, I'm going to get this variable, that variable, and that variable. It implies this particular causal structure. I'm going to compute some bounds on particular connections, and I'm going to fit that to the next program and so on.
Yeah.
Because you don't have to make assumptions about sparsity anyway. Actually, you can just say everything is fully connected and can just add a constraint saying some connections are weaker than others.
Yeah.
Although expressing that in the continuous case may not be that straightforward.
Mm.